Today we'll discuss about the principles of maximum likelihood detection, which is a general and optimum method for detecting the transmitted signals, time limited signals conveying information through the symbols. Okay. And we will gradually consider a somewhat special class of communication channel where we have only additive white Gaussian noise, okay, and the channel is a linear time invariant channel without manifesting any interference and other problems. Okay. Now, some of the assumptions I have listed at the beginning, that in fact we have discussed about a few of these assumptions already, that one of the M signals, by this time it should be clear that our basis of the design of the transmitter as well as the receiver, okay, is going to be that we will consider symbols, M symbols, M, capital M number of symbols. The number of symbols may be 2 or any larger value, and then this M signals symbols will be transmitted through M signals, time limited energy signals, and we know that Gram-Schmidt orthogonalization procedure can be chosen to design these M symbols to a good extent. And then we also assume that these M signals, one of the M signals will be transmitted in each time slot of t second. That is the signal duration or symbol duration. Okay. And this issue also we discussed earlier, that all symbols, I put a note of interrogation here because here I am using, from henceforth I will be using the words interchangeably, equivalently, that symbol, signals, okay. Symbols, they convey information, okay, can be generated by grouping the bits, serial binary bits, okay, those are the symbols, but we now know how to represent the symbols by some time limited signals, okay. So the symbol duration is the signal duration for a particular symbol, which is t second, and what I am saying is that all symbols are equiprobable. We have good reason to assume that, okay. That is the probability of SIT, here I am deliberately putting the signal notation, the probability of the ith signal, that is the probability of the ith symbol, is the same, is 1 upon m. It does not depend on which signal or which symbol is being transmitted. This is true particularly when we are talking about a continuous transmission stream, reception scheme, where the incoming bit sequence is very large. For a very short transmission of a few number of bits only may not follow this one, but our system design is for a system which will be continuously on and will be transmitting symbols after symbols. So this is valid asymptotically. Then we are also assuming that the additive white Gaussian noise process, AWGN, in short, the process I am indicating as capital W as a function of time. It is a time varying process. It is a stochastic process. You have heard this name by this time, I believe, in the tutorial class, right? So this additive white Gaussian noise process I am indicating as WT, and you know that if I observe the process not for its entire duration of life, okay, which may be impractical really, if I observe it over a very finite duration of time really, what we get is a kind of sample function of that process really, of the random process, and that sample function I am indicating as small w as a function of t. Here the small w of t is going to be more useful for our mathematical analysis, and for the whole noise process we are assuming that it is a zero mean process, which is the case usually for thermal noise, okay. It is a zero mean process, and the power spectral density, okay, double sided one over both positive and negative half of the frequency band, okay, is n naught by 2, so that the single sided noise power spectral density is n naught, okay. What is going to be the unit of n naught incidentally? N naught is the power spectral density. Pardon? Watt per hertz, yeah, that is the unit, okay. The unit of n naught is watt per hertz. It may be microwatt, nanowatt, a very small value, but whatever it is watt per hertz, okay. And Wt is a noise sample function which may occur during the observation time of capital T, okay. Yeah.
Sir, is it meaningful if we thought of like plotting AWGN on the vector space, as in like plot AWG and the vector space phi 1, phi 2.
Right.
Will it carry some meaning as in is
Yeah,
it
it does.
possible for one
Yeah, it is possible very much. In fact, it is done like that. In fact, narrow band noise process can be, I mean, visualized quite in a similar line as that of a narrow band signal. Okay, though in fact both are fundamentally random, is it not? The signal, a random signal, which is the narrowband baseband signal, equivalent baseband signal, is also something random, but that's a desired form of randomness. Really, we want to preserve this. We want to transmit from one place to other. I think I used the words earlier. Whereas noise is, only thing is that that's something undesired. But so long as they are both narrowband, the technique can be used.
So in
So
that case,
yes,
how
it
will
can
we
be.
plot AWG and on the C vector space?
So in fact, AWGN also I can say, if I consider again a two-dimensional vector space, I mean signal space, I can again say that the noise also will have two components. Now using our language of the complex equivalent form of a baseband equivalent form of a narrowband signal, I can say it will have a real component and an imaginary component, Ni and Nq. Yes.
So the point what I'm saying is like so it will be like continuous curve rather than being one point. So because we have a
Well, that's a good point. In fact, I missed last time really. That's a good point. Is that when you talk about signal, we visualize that okay, it's a function of time. In fact, I indicated as Si as a function of time t between 0 to capital T, isn't it? So the signal, our first hand impression is that how it changes with time is of interest. It's fine really, but when we visualize the signal space, okay, the signal space was defined in terms of the basis functions, and each point in the signal space we said is a vector. Okay, it was not necessary to continue with the time description really. Okay, in fact, if you think back about the correlator structure as per our Gram-Schmidt orthogonalization procedure, the correlator output we get, okay, at the end of the observation duration of 0 to t, is it not? You multiply with the basis functions, okay, I mean a signal, and then you integrate, you get the corresponding coefficients. These coefficients are obtained at the end of the integration period of t, duration t. So the coefficients, they form the vector basically. This S11, S12, S3, S13, etc. So they are scalars. We get these coefficients once in one after one time interval. That's is the implication of this first assumption here really. So when you talk about the image, I mean signal space, it is not in terms of directly time. Okay, we plot a vector in the signal space. So the time dimension is not there. It need not be there. Okay. In fact, subsequently, when we talk about the modulation technique specifically, and we think of drawing the modulated waveform, okay, we have to bring in the time dimension. We'll do it appropriately. It can be added on. Okay. For the moment in the signal space description, time is not important because it is assumed already that the vector components can be obtained if something unknown symbol is coming. The corresponding vector components will be obtained only after correlation with the basis functions and integration over the time interval t really. So once every t second, the correlator outputs will get updated.
But here in this AWG and assign WT, so that is a function of time.
This small wt.
That means
Yeah, yeah.
this
So
constant noise is also changing with respect to time.
it does change. Yeah,
In
it is.
that case, how can I take the symbols independent irrespective with respect to time? Because if I'm
His question is,
it's changing,
this noise is changing with time. So how can I?
that is I will keep changing.
So this will keep on changing. So how can I repeat the last
How
part?
can I take the
I mean, how can we actually get the basis functions for and correlate them to the basis functions of the symbols? I mean, can we represent the noise vector with respect to the basis functions that we have found out for the signals, for the symbols? Can we express the noise in terms of those basis functions?
the
Or we
basic
have to
thing
find
is
out a new set of
like
basis
we
functions
can't
for
have a point representation for noise basically. We'll have to go beyond a point representation.
Yeah, I think I have some diagram, indicative diagram. I'm addressing this issue. That's a very good point, really. Very good point. In fact, I'll politely say that we have defined. We have so far defined what I said is a signal constellation, signal space, and a signal constellation, and we can map the received vector, which is the transmitted symbol plus the noise, also within in the signal space. That is possible really. Okay, I'll explain a little bit more how it is possible at that point really, and then go further. The summary answer is that yes, it is very much possible, because first is the basis of how do I get the coefficients. and for that the correlator structure is used. The correlator structure does not increase the bandwidth of the incoming signal, it only brings it down to a lower frequency signal. So even though the actual noise process will have a very large bandwidth, we know the noise has got theoretically infinite bandwidth, isn't it? Practically several hundreds of gigahertz at least, okay. But the noise which will matter for our system, which is a narrowband transmission system, that you should never forget that we are talking about narrowband transmission system only. When my modulated signal is designed over a narrow bandwidth around a carrier frequency or not, even in the baseband level, I mean the noise that is going to disturb us is only that in-band noise really. So when you say that our corresponding noise of interest which is going to disturb our transmission is a narrowband noise, I can, if I like, I can decompose it in the real and imaginary form in the complexity equivalent baseband form as well really. So ultimately it is possible to represent the corresponding noise which is going to matter also in this signal space.
It is time variable.
No, see, unfortunately I am not having the diagram of the, let me draw it 1 second really. See, in the signal space, the question is very important. Let us understand this point. See, when I defined a signal space, I did not in fact even say that okay, the signal space is defined with respect to time, did I? I also did not say that how the signal space changes with time, isn't it? What I did simply is that okay, the received some a signal Si, okay, can be represented in terms of a signal vector. SIT can be represented by signal vector, and the components of this matrix were, isn't it, Si1, Si2 up to Sin, isn't it? These are scalars. When do I get these scalars? We had an expression for this Si1, Si2 as well. What was that? Integration of SIT phi j t dt. So you get the scalar only after you carry out that integration. Okay, so your SIT may be changing with time. SIT does change with time, with t. It is 0 capital T. Okay, but you come out with the scalar values only after integration at this point. So once the integrated output you have sampled at t equal to capital T, you get these scalars really. So do they have any implication of time if I consider only one symbol? No, and that's what I plotted in the signal space. So if I am worried about one signal over a duration of 0 to t, I need not talk about any time here. In his mind the time idea is there, and it is actually there because we are talking about transmitting signals after signals, one symbol after the other one, and noise is always present, so it is always changing. So the actual process is continuous, isn't it? So his point is valid ultimately, is it not? But the point is that when you talk about this detection strategy, we will see that we have a fundamental responsibility of detecting or deciding about one symbol when the corresponding SIT has been received. See, our issue in the receiver is to decide at this point, not earlier. One should not think of taking decision midway in between, unless there is some special reason really, okay, and that decision is not going to be best perhaps. So the decision has to be taken once in t duration, capital T duration. So for decision making, I can very well make use of this constellation diagram without talking about time. What is going to, and if I come out with a structure wherein the noise also gets restricted, I also get some noise output at this point. See, noise has got a zero mean, isn't it? But over which interval? If I keep on observing the noise which I may generate from any say Zener diode or resistor or any other dissipative component really, you have not tried that ever really. It's very easy to generate thermal noise and see it on the CRO even. Oh yeah, okay, I'll give you a small problem later on really. It's a very simple circuit you can wear and see that yes, noise is visible on the CRO even, and it fluctuates like it's sometimes drawn in the book. The point is that when you say the noise process has got a zero mean, okay, noise is being viewed as a statistical experiment, and the mean will be exactly zero when the observation, when the process is complete. That means when noise ceases to exist. When is that? At infinite time really. Okay, so if I have the patience and the capability to observe noise for an infinite time duration, then only the mean should be precisely zero. That this does not mean that if I observe noise over a duration of 0 to capital T, which is what I am going to do in my receiver, in my receiver I have to take a decision about a symbol once the corresponding energy is over. That means every t second I have to take a decision. So I will be observing noise only over a very small duration of t second, capital T second. Nobody guarantees that the corresponding mean of that noise sample function is 0, no, isn't it? So we'll see that in our receiver structure we again will be using some kind of integrator or something. So noise, this we will be finding essentially some average of this noise process, okay, and we'll take a decision. And this noise is not going to disturb the noise of the corresponding, disturb the transmission of the corresponding next sample really. A new sample function will disturb that, okay. So this is a very good example. I mean his question is very well taken, because this is where on the one hand we will be talking about some statistical feature whose description does not necessarily need a time description, okay, while our very purpose of transmission reception is in time, basically is a time sequential process. We transmit one symbol after another. So one has to correlate these two, and that's what we do by defining a special kind of statistical process known as stochastic processes, where the random process we describe as a function of time really, okay. So we will also do that in a limited manner when it comes to. Well, let's get back to my topic of maximum likelihood detection. The assumptions, I think they are okay now, okay. This WT noise sample function is the sample function which I am going to add with the transmitted signal, okay. This sample function I am interested in this duration 0 to capital T, okay, and this process will have infinite number of such possible sample functions. That should be understood. Now I am following that classical approach of statistical description of the whole process. So I am defining again a received random process, capital R of T. This is a stochastic process, okay. This is a statistical experiment being conducted and will be observed after a duration of capital T. So capital R of T I am indicating, I am using to indicate the received random process. What is my received random process? My process is that I am receiving signal coupled with noise, okay, and this random process also will have a great number of infinite number of possible sample functions. So one sample function I am indicating as small r as a function of time. This time you can see the function I am interested is over a time interval 0 to capital T, and we may write that this expression I am sure most of you will accept that yes, it is so obvious really, that R of T, the sample function of the received random process, is the transmitted signal SIT, some ith signal plus the noise sample function. Is it not? Is there anything wrong in this expression? Very intuitive, okay. And because I have considered my noise to be additive, which is usually so I can write this. Huh?
What can be the other form of noise if it's not additive? I mean, you say that it's usually additive.
In fact, I will say mostly additive. Okay, there are other situations where I mean we did mention about some kind of fading, isn't it?
Sometimes it gets
Signal gets faded because of various reasons like multipath, scattering, etc., etc. Now, sorry, though the process is not fundamentally due to any kind of thermal noise there, but after modeling one can see that this kind of fading may result in an envelope fluctuations very fast really, and after this is the basic first level study, okay, and this study, this discussion forms the basis of many subsequent systems which may be more complicated in nature. So after mastering this technique of AWGN system analysis, now when you try to analyze a system with fading etc., you may develop a tendency of saying that well, that envelope fluctuation, very fast fluctuation also is some kind of some kind of noise, say, though it's technically not correct that way. Some kind of approximation may be made there, okay, and then you may find that that fluctuation is fundamentally multiplicative in nature, okay, because that's fundamentally not due to thermal noise. So long as thermal noise is concerned, it is additive, okay. So long as your transmission propagation channel is linear, let me put it that way again, okay, linear, okay, and especially time invariant, you get this additive noise effect only, okay. So Is this expression fine? So, I can say that this is simply the received signal is transmitted signal plus noise in a simple form. Okay. In a better manner, the received sample function is the sum of the transmitted signal over the duration and the corresponding noise sample function. Okay. In fact, it is very clear that if say I is 1, if the S1t, the first signal was transmitted, and if I observe it for the first time, I may get a sample function Wt. If I again transmit S1t, I may get a different noise sample function, isn't it? So, I am retaining all the randomness of the noise, I am not disturbing anything. Okay. Now, this is a starting expression. Now, then what should be the job of the receiver? The receiver here stands for a demodulator or some kind of decision making, everything included. What should the receiver do if the received sample function is going to be of this form? So, I have my description here, you can contradict, is that to make best estimate of the transmitted signal SIT upon receiving RT. Is it not? What you receive is RT, okay, at a distant place, and your job is to make an estimate, okay, which is some kind of decision ultimately on SIT, what symbol was, what signal was transmitted, isn't it? So, we will elaborate on this point. So, towards this, so I have an issue where the transmitted signal got added with some kind of noise process, noise sample function. So, I have to extend my previous idea of signal space as we were going to discuss some time back. So, now I define formally what is a signal constellation. In fact, we mentioned some time back that the signal constellation is nothing but the signal space when all the m signal vectors are shown as m signal points in the signal space. So, I can say it is a collection of m signals. Just to remind you where from we get these signals, within bracket I have said or message, even one can also say collection of m messages, you will find these descriptions in many books. So, it is a collection of m signal points on the signal space, is a signal constellation. Is that okay? Well, so if this is my two dimensional signal space, if I show the points as S1 here and S2 here as vectors, okay, then I can say this now is a signal constellation with two signal points. Okay. Now, I would like to use the same signal. See, this signal constellation is defined once your transmission scheme is defined, isn't it, in the transmitter somewhere. I would like to use the same signal constellation for the purpose of detection or for the purpose of reception of the signal. Towards that, what I will do is that I will try to place the received sample function RT on the signal constellation. In your signal constellation, you may have a few defined points, say S1, if I call this point as S1 specifically, S2 and S3. Then on the same signal constellation, I would like to also represent the received signal sample function R of t. Okay. Now, can I really represent R of t here in the signal constellation directly? Pardon? We do not know. Okay.
Is it necessary that the received vector and therefore the noise vector can also be expressed as a linear combination of the basis vector?
I think that is a better point to start. His question is, you had some question on probability.
How to represent the probabilistic presence of the noise same basis functions like phi 1 and phi 2. I mean,
well,
noise is expected to be more jagged and more of a very different form than the symbols, than the regular symbols that we are considering.
Right, right.
So how do we express them in terms of the same basis function?
In fact, it is not necessary at the moment to really express the corresponding noise portion small wt. See, this simple job of the receiver can be viewed from different angles. One is that, see, fundamentally what we receive is r of t. There is no uncertainty about this. I receive some r t when if I observe over an interval capital T, no uncertainty involved. But what I receive is uncertain because r t has got two components, both are fundamentally random, is it not? Okay, SIT is a random thing. My purpose of the receiver is to detect, take a good decision of what SIT was when I also had WT coupled with that, is it not? But fundamentally both of them are random. So I have observed something which is the addition of two random sample functions. Is that okay? Now the strategy may be, one strategy may be that what I know more is that SIT part, this first term will have only one of the m possibilities, whereas how many possibilities are there for WT? Infinite. So it may not be a wise idea to really find out WT precisely or really try to express WT precisely, because it has infinite possibilities. It is going to be very frustrating really, even if somebody tries to precisely try to find out what was WT, so that a naive idea may be that then after I find out WT, I will very comfortably write that SIT, if I call that even as estimate, is R of t. What I have received, minus W of t. This idea, it is very naive, is going to be very impractical and frustrating. Is that okay? Because this noise has got infinite possibilities, this has got some finite possibilities, m number of possibilities. So trying to find the noise in the observed interval of capital T and then subtracting it from RT, whatever I have received, is not a good idea. Is that okay? And is, yeah, just one point before, just one point, hold your question really. So the idea of trying to express WT completely at this moment is not very sound. There may be better ideas really. In fact, the technique is somewhat better. We are not, it is not necessary to express WT completely, even to represent the received, a corresponding received vector for R of t really. I will explain that. Yeah.
So what I was saying was, if we have like a complete representation of WT, in such a case we can make an approximation of RT will be, like we can make an approximation of what range will RT lie. So anything beyond that range we can elect as not being of S1T.
Well, I think he is trying to help me really, okay, in formalizing what the maximum likelihood detection process should be. Yeah, good. Okay, let's wait for some time. I'll come to your conclusion to a good extent in a formal way. Yeah, yeah.
Even then, sir, there is no, we cannot say for sure that RT can be still expressed in terms of the same basis vectors, because when we design those basic vectors we did not take into account RT.
No.
So then how can we say for sure that RT can also be expressed as a linear combination of the same vectors?
Let me take an example. Okay, we had, okay, consider this signal space, two-dimensional signal space. Okay, this goes very well with our description of a narrow bandpass signal. You remember, we represented a narrow bandpass signal by its equivalent low pass complex representation. Okay, so a real signal S of t, okay, which was in a general form, sorry, narrow bandpass signal we represented earlier as, in a general form, at cos omega ct plus some phi t, is it not? This is a real signal, the bandwidth is smaller. Okay, so how did we represent it ultimately? After some direct multiplication etc., we came up with an equivalent complex low pass description of this. You remember, low pass equivalent description, which we represented as ui plus uit as a function of time plus j u q t. We didn't have any problem in understanding why j was there, because we had two carrier components, cos omega ct and sin omega ct, is it not? And we know that they are in quadrature, they are the same frequency, they are in quadrature, isn't it? I think this is a good example really to understand that in this case we were talking about a two-dimensional signal constellation, okay, two-dimensional signal constellation where the dimensions phi 1 and phi 2 were related fundamentally to cos omega ct and sin omega ct, okay, and then the signal s of t, okay, was viewed as ui and uqt, okay, briefed of the corresponding dimensions of cos omega ct sin omega ct. Now if I just express it in a somewhat different manner with scalars such that the cos omega ct portion has got unit energy over the symbol duration of t, I can do it very well really, okay. Then with a scaling, this uit and uqt essentially does represent as if phi 1 my basis function was cos omega ct portion, something proportional to that, the whole energy has to be unit, because by definition our basis function has got unit energy, and this one may be our sin omega ct related to that, okay. And then I can write that the signal corresponding signal point, signal vector was nothing but ui in this direction and uq in this direction, isn't it? Ui of course not this ui directly, because ui is a function of time, ui is a function of time. What we have to, how do I get the corresponding coefficients really?
A cos theta and
You integrate that, yeah.
so in this case ui is like a cos theta t and sorry.
No, no, my point is that the signal space does not represent anything in time. So what I do, yeah, the integration, the way I got the coefficients si1, si2, si3, isn't it? So I get that corresponding values for uit and uqt really, okay, and I can represent the signal point for this st in this two-dimensional signal space, okay, fine. Now my received sample function r of t, today I said that let it be s of t plus wt. So my signal is a narrowband signal. I would like to ensure that my received sample function is also a narrowband signal. R of t is a narrowband signal. That I can do by design. See, when I know that my signal is over a narrow bandwidth, why should I unnecessarily invite unwanted noise? Okay. So somewhere I'll put a filter appropriately such that though the actual noise process in the physical world might be occupying a larger bandwidth, I will pick up only that band limited noise. That's known as band limited noise really. So essentially my WT process also is band limited, and I can say it's a narrow band noise process. How much is the bandwidth is dictated by the bandwidth of the signal, okay. So this WT also is a narrow band process, okay. And if WT is a narrowband process, if I wrote a signal like this, I can make an attempt. I guessed that this was covered in your earlier analog communication course really, that this narrowband noise process can also be expressed in this form. If I am using a carrier omega cos omega ct and sin omega ct for my signal, I can visualize that this narrowband noise process is also centered around w cos omega ct and sin omega ct and centered around the frequency of fc, okay. So I can equivalently have an equivalent noise description of nit plus j n, sorry, small n qt. There is no problem, because again this nit, if you visualize, is a slowly varying random very slowly varying noise, because my noise actually has been filtered. My transmitted signal st was a bandpass signal. So assume that at the receiver, before the signal is taken for decision making etc., a very narrow bandpass filter, ideal filter has been used, so that the signal bandwidth is allowed and the signal comes in, and along with the signal portion of the noise in the frequency band also comes in. So that is a band limited noise. So the corresponding components in the low pass equivalent form nit and nqt, again like the signal component uit and uqt, will be varying slowly with time, slowly with reference to the carrier frequency variation. So nit and nqt, they are also essentially slowly varying functions of time. And now here is a difference between what he was saying some time back, that noise is a remarkably different looking zigzag kind of signal, accepted when it gets added to the signal. But when I take this noise corrupted signal for processing, I do it only after appropriate bandpass filtering or appropriate filtering. So if you visualize that noise somehow, try to see it in the CRO, you will find that fast changing nature of the noise has decreased. The noise is also changing much slowly, because I have cut much of the frequency band of the noise, isn't it? So the low frequency noise need not change so fast compared even to the symbol change really. It will be much slower if you try to visualize. Anyway, so summary is that yes, it is possible to represent noise, okay, after appropriate bandpass filtering, to represent the noise following the same technique of equivalent baseband representation, and hence I can put even the noise sample on my signal constellation. I had a discussion of the, I mean this diagram, let us say, suppose you had transmitted S1 from your transmitter, and in the process some noise component got added, okay, and at the receiver end you have done some appropriate bandpass filtering, so that my small wt is a narrow band noise process. Then if I want to represent this wt, the corresponding noise vectors, I can represent it. The point is that till I know completely wt, I cannot exactly say that it is here, but I can say that it may be here, it may be here, it may be here, it may be here as well, here as well. But just now we talked about Gaussian distribution. This noise follows Gaussian distribution even after filtering. Okay, so it is more probable, if I now talk about probability, it is more probable that the noise point, signal point, I won't say signal, that corresponding noise point most probably will be somewhere here. Where it is, I do not know, I need not know, because as I said, I mean it is a futile exercise to try to determine exact form of small wt. Okay, but I can say that it is more probable that the noise sample is somewhere here, closer to this origin of zero energy, because noise has got zero power, I mean zero, sorry, not zero power, I mean zero mean. Now, and this is a very small interval really, the corresponding energy is also going to be very small, though the noise point may be even here, is it not? By probability, I can say that it is possible, but the probability is very, very small. So that at least this kind of description I can give for the noise really. So following that, now let me say, I'll just stop in a few moments. In our discussion, what I can say is that if SI is here, then after noise, hopefully that the noise component is not unusually very large, whose probability is very small, we know it follows Gaussian distribution. I can say the noise corrupted received vector, which corresponds to a band limited R of t received sample function, will be somewhere close by. So see, just to show that let us consider that the received vector point is here. It does not, I am not saying that it is indeed here, it is not that. Okay, if you say the no sir, let it be here, I say fine, draw there. Okay, it is unlikely that the received vector is here, though it may happen very occasionally. So somewhere I can say that okay, the received vector, the received sample function, okay, R of t, can also be represented by a vector somewhere in the signal space. That is what is necessary for the moment. So I can represent the received vector also in the same signal constellation, extending the concept a little bit. Okay, unless I do not know the exact form of wt, I cannot show where exactly it is, but that is not necessary again. But I can say that this will be somewhere around SYT, or it may be further away also occasionally. Our idea is to formulate a basis for what should my strategy for best decision making. That is what is the proposition for maximum likelihood detection. I think we continue in the next class. Okay. Only point is that if I really knew about this location of R, I could, from this signal constellation description, I could find W bar, the corresponding noise vector, isn't it? Okay. Any other question at this moment? Thank you.